it is my pleasure to virtually introduce you to our keynote speakers. Mr. Aung will be sharing his insights on designing more resilient and less vulnerable buildings using performance-based design approach. So a brief introduction to our second speaker. Mr. Aung is currently the Executive Director of AIT Solutions. In over 16 years of his professional experience, Mr. Aung has been involved in over 150 tall building projects across Asian countries, including Thailand, the Philippines, India, to name a few. In these projects, Mr. Aung has led the structural engineering team at IT Solutions and provided solutions and services in performance-based seismic design, wind engineering studies, and real-time structural health monitoring. Apart from projects, Mr. Aung has authored and co-authored several research papers, some of which include smart system for smart structures, performance-based seismic design of reinforced concrete dual system building, smart system for structural response control, and lastly, preliminary design of tall buildings using artificial neural networks. So without any further ado, let's give it up to Mr. Aung.
Okay, good morning, everyone. Today, I will present our practice in carrying out performance-based seismic design of tall buildings. So when we carry out the structural design of buildings after completion of architectural form development, we have to develop the structural system. Generally, in the code, commonly used structural systems are bearing wall system, building frame system, jewel system, moment frame system, and cantilever column system. They are for the seismic force resisting systems. Bearing wall system, we design for the walls to carry the 100% of gravity loads as well as the 100% of lateral loads. In building frame system, we design the walls to carry 100% of the lateral loads and the frame carry only the gravity loads. For moment frame, it carries both gravity and lateral loads. But dual system, walls and frames are carrying lateral loads together. But for cantilever column system, we use for the small structures like the garages. So in tall buildings, most of our structural systems are based on those common structural systems. In ASE 7, there are more than 80 types of structural systems. Here, there are some structural forms that we normally use in the design of tall buildings. Sometimes we use the bearing walls. If the lateral stiffness is not adequate, we also add the outrigger systems together with the bearing walls. And also we use the dual systems which comprise of shear walls and moment resisting frames. So let me briefly talk about the seismic design concept. The current seismic design, the building code's objectives are to prevent the buildings from causing large-scale loss of human life and in earthquakes. So our main priority is safety, public safety. So when we design the seismic design of the buildings, for the normal residential buildings, we allow damage in the buildings under strong earthquakes. We do not design the normal buildings to remain elastic or no damage at all during the strong earthquakes, because those strong earthquakes may not happen during the lifetime of the building. So if we design to remain elastic, in that case, our design may not be economical. So what we do is we allow some damage, but the building should not collapse under strong earthquake. And also the buildings should be serviceable under frequent earthquakes. So in this figure, x-axis is the lateral displacement roof drift of the building, and y-axis is the seismic force base shear of the building. So if we design the building, let's say, if we design the building to remain elastic, the force and the displacement relationship will be linear as shown in the blue line. If the force increase, the displacement increase linearly. But when we do the design, we do not design for the elastic base shear. So we design elastic base shear VE. So when we design the building, we reduce the base shear by the response modification coefficient, which is based on the ductility and toughness of the structural system. So we reduce the base shear VE divided by R, and we got the design base shear. There will be minimum base shear, design base shear requirement in the code. So after getting the design base shear, we design the building and we provide the longitudinal reinforcement in the beams, vertical reinforcement in the columns for the flexure response, and also shear reinforcement in the members. And we design those reinforcement based on the design base shear V. And also we provide the detailing requirements according to the structural system that we selected. So one strong earthquake happened, the actual base shear will be more than our design base shear. So when the members reach their yielding capacity, they will start yielding. So the structure becomes nonlinear. The structure behaves inelastically. The force is not increasing substantially like elastic response, but displacement increased substantially. So to carry the gravity loads on our structural system and the large displacement, the ductility is important. So we have to provide the ductility, the ductile detailing requirements in our structural systems. So in our analysis, normally we carry out the linear analysis when we do the code-based design. So when we apply the design base shear V, we will get the displacement, which is delta E divided by R. So our analysis domain is only in the yellow region, only in the elastic analysis domain. We cannot capture the actual response of the building, which is inelastically, which has the inelastic response. So the inelastic response region, the purple region, is not explicitly simulated or checked in our normal code-based design procedure. So we just implicitly, we just assume that if we design the building according to the design base shear and provide the ductile detailing, our building will not collapse under strong earthquakes, and also our building will be serviceable under frequent earthquake. But there is no explicit evaluation in the analysis. And another thing is, after reaching the yielding capacity of the members, the base, the shear demand still increase. The curve is not flattened suddenly. There is a overstrength effect, which we normally estimate with the overstrength factor omega naught. That overstrength effect is coming from the material overstrength, which is in which we use the nominal material properties in our design, but actual properties of the materials will be more than that. For example, the rebar strength, yield strength, the nominal strength, and the actual test strength will be different. Not only that, we have the safety margin in our design. We leave the safety margin TC ratios 0.8, 0.9 in the design of members. And also we have the load factors, overstrength. We have the load factors and also strength with reduction factors phi in our design. Those effects generate the overstrength and the it will increase the base shear, which will reach the Vmax. To estimate that maximum shear demand in our system, we have to multiply our design forces with omega naught. Those forces, those amplification we mainly use in the important structural systems to resist the maximum demand forces, not all the members. And also we estimate the inelastic lateral displacement or drift using multiply with the CD deflection amplification factor, because we have to check our lateral drift whether it is within the acceptable limits or not. In between 1987 and 1994, there are several earthquakes in California. So Structural Engineering Association of California and FEMA, they developed the framework to enable the engineers to design the buildings with predictable seismic performance and also enhance the performance objectives in the basis for design relative to those underlying in the contemporary building codes. So that project called Vision 2000. And then they developed the design procedure, which now we call it performance-based design. So compared to the code-based prescriptive design and performance-based design, in code-based design, we have to follow the prescriptive criteria mentioned in the code. And the engineers do not have the ability to evaluate the actual performance which is intended by the code. And also there are limitations in the use of structural systems. So mostly the code-based procedures, we presume if we conform the building code, the performance will be obtained. On the other hand, in performance-based design approach, we check the building performance explicitly under different levels of earthquake. And also we can substantiate, we can ignore the code prescribed requirements if we can prove that our building performance is meeting the code intended objective. And also if we want to use the innovative structural systems or devices, we can also prove with the performance-based seismic design approach. Finally, performance-based design can also provide us the cost-effective design. For example, in ASCE 7, if we want to use the bearing wall systems in high seismic zone, there is a height limitation, 160 feet. If we want to use in the tall buildings, we cannot use those bearing wall systems. Tall bearing shear wall with the flat slab system, we can use only for the 16-story building. So if we want to use those systems, we have to prove by performance-based design approach. So in this architectural form, if we design according to the code base, we need to use the dual system, which has no height limit. So in that case, we need to provide the moment frame and the shear wall. But if we can prove with the BBD using that bearing wall system only with the flat slab, we can achieve the cost-effective design. Not only that, we can have the clean structural system compared to the dual system. So this is the comparison of the structural system with the moment frame and the flat slab. Another thing is the overstrength factor, omega naught. If we have the transfer system where the discontinuity happen in the lateral system, in that case, we have to design those members with the overstrength factor. So in overstrength, in the code, overstrength factor is about 2.5. But if we design with the performance-based seismic design approach, we do not need to consider those prescribed factors. We can explicitly estimate the force demand in those members in the nonlinear analysis procedure. And also we can use the innovative systems like the dampers, like viscoelastic coupling dampers or phase isolation. So we can prove those devices' effectiveness using the performance-based design approach. In terms of cost effectiveness, for example, in the shear walls, we have to provide the confinement reinforcement at the boundary zone in the code-based design approach. But if we can prove that in our BBD analysis, nonlinear analysis, if the shear wall axial strains are not large, we can relax the shear wall confinement in those stories. So it will have the cost saving. So here is the comparison between code-based confinement layout and the BBD confinement layout. In BBD, the confinement is relaxed and it is not congested. It will also help improve the constructability requirements. So when we carry out performance-based seismic design, we need additional information compared to the code-based design. Normally, in the code-based design, we have to prepare the design criteria, which we call basis of design. In BBD also, we need to prepare that document, but we have to consider the seismic input, additional seismic input information, and also performance objectives and acceptance criteria based on BBD procedure. And geotechnical investigation, normally we conduct in the code-based design as well. So from geotechnical investigation, we have to get the soil type for the seismic loading, allowable bearing capacity. If there is a soft soil site with the liquefaction potential, we have to check. And important one is in BBD, we have to engage another consultant. We call it PSHA consultant. We have to conduct the site-specific probabilistic seismic hazard assessment. So that consultant carry out the seismic hazard analysis and provide the structural engineer with the recommended response spectra for service level earthquake, design earthquake, and maximum considered earthquake. And also they provide the ground motions to be used in the nonlinear time history analysis for maximum considered earthquake. If our site is at the soft soil site, they also conduct the site response analysis to check the amplification of the amplification effect of the soft soil layers. Normally in code-based design, we amplify the soft soil effect with the code prescribed factors FA, FE value according to ASCE 7. For the tall buildings, wind tunnel test is also important. Wind tunnel consultant provide the floor acceleration and also the floor-by-floor wind load to be used in the structural analysis. So normally they provide the 10-year return period wind for service level wind check, for the story drift, lateral displacement, and for the ultimate strength design of the members for calculation of reinforcement, they provide the 700-year return period wind. And also they conduct the natural frequency sensitivity study because our finite element model's natural period may not be exactly matching with the actual building natural period. So they're changing the natural frequency of the building and provide the force demand and acceleration. Here are some good reference for performance-based seismic design and also wind design. Currently, the latest BBD guideline is LAD BSTC 2023 with 2024 supplements. This is from Los Angeles Tall Building Structural Design Council. Together with those guidelines, we also use the ASCE 41 guideline in modeling for the nonlinear modeling parameters. So in seismic hazard assessment, PSHA consultant normally provide three response spectra, which is maximum considered earthquake, which has 2475-year return period with 5% damping, and design earthquake, which is 2/3 of MCE, and service level earthquake, which is 43-year return period. But for service level earthquake, the damping varies with the height. For the tall buildings, damping will not be always 2.5% damping. It will be lower than that. Maybe it is about between 1.5% to 2%. So for seismic performance objective, this is the code minimum intended objective. We have to check for service level earthquake with the performance objective to satisfy the serviceability requirement. The structure has to remain essentially elastic and minor cracking in the concrete and damage. For maximum considered earthquake, we have to check for the collapse prevention requirement. The structure should not collapse, and the extreme earthquakes, it will have damage, but may or may not be repairable. So in PBD procedure, first we have to get the geotechnical investigation results. And also after getting the geotechnical investigation results, we have to engage the PSHE consultant and provide the geotechnical assessment to PSHE consultant. During that time, we can develop the structural system in schematic design stage. After getting the structural system preliminary finite element model, we have to provide the dynamic properties to the wind tunnel consultant, model analysis results to the wind tunnel consultant. So wind tunnel consultant will carry out the structural load test and use post-process their results with those dynamic properties and provide the wind loading to the structural engineer. So structural engineer will carry out the initial elastic design using that wind loading and SLE loading from PSHE consultant and get the initial reinforcement. Then carry out the nonlinear evaluation, and create the nonlinear model and check the MCE level evaluation. So in design process, in the initial design stage, structural components are designed for the maximum of wind and service level earthquake demand. But some structural members like shear wall, shear design, if we determine the shear wall thickness based on the wind and SLE demand, it may be small. It may not be adequate for the MCE demand. So those kind of components, we check the demand based on the response spectrum, MCE level response spectrum analysis using experience factors with our value. We divide by the MCE elastic demand with the experience factors, R values. Then we get the reinforcement information to be used in the nonlinear model. Then in MCE evaluation, we create the nonlinear model and analyze the time history analysis. So in SLE evaluation, we have to conduct the response spectrum analysis and create the linear FEM model. And accidental eccentricities are not considered in service level evaluation. And critical damping is between 1.5 to 2.5%. And also, we do not consider our omega naught rho factor and CD factors. And also, we do not scale down the SLE base year to the to the equivalent static base year with the R factor. Because in SLE level earthquake, we want to design the building to remain elastic. So there is no scaling for base year. For acceptance criteria, we check the drift limit and also DC ratios for depending upon the deformation and force control actions. For drift limit, we use 0.5%. For MCE level evaluation, we conduct the nonlinear time history analysis. Mostly we use 11 pairs of ground motion record. And for damping, we use 2.4% constant modal damping with small amount of relay damping for unmodeled energy dissipation. And we use the average demands of 11 ground motion records. So in nonlinear response and modeling, we have to model the backbone curve parameters for our structural components. For example, in this figure, x-axis is rotation of the beam, and y-axis is the moment demand. So x-axis present the rotation in radian. So during the laboratory test, if we reach the yielding moment capacity, the moment demand doesn't increase significantly, but rotation is increased. So we apply the cyclic load and then we develop the backbone curve. So normally structural engineers familiar with the strength capacity check, calculate the moment demand and calculate the moment capacity. We understand that. But for the rotation demand and rotation capacity, we are not familiar with. This rotation capacity is determined mainly from the laboratory test. We can generate the rotation, we can calculate the moment rotation capacity based on the moment curvature curve section analysis, but we normally use the laboratory test results because it is a cyclic loading. It has the effect of the shear demand as well. So these are the sample test figures for different rotation demand level. So we need to know what is the damage state of the rotation demand as well, because we are checking the rotation in some components in performance-based design approach. So when we classify the actions for the deformation control and critical deformation control and force control action, we have to think based on their response. So if the response is tactile, for example, flexure response of the beam, after yielding due to flexure bending moment, the beam will not fail suddenly. So we consider that action as a deformation control action. For the brittle actions like shear response, shear failure, we consider as force control action. So for deformation control action, we can get the backbone curve parameters from the ASCE 41 document. Here are sample parameters for the backbone curve for the beams. So on the red box side, there are modeling parameters to develop the backbone curve. On the right side, in the blue box, it is the acceptance criteria to check whether our rotation demands are within the limits or not. So if we check for the collapse prevention performance level, we have to check with the CP performance criteria. Here are some acceptance criteria for global response as well as the local response. I will not explain details. Professor Iswandi already showed the acceptance criteria in his presentation. So after analyzing the nonlinear time history analysis, we have to check the global response first. We have to compare the base shear, story drifts, whether the results are reasonable and acceptance within the acceptance limits or not. For the base shear here, I compared the base shear for elastic MCE base shear, inelastic MCE base shear, and SLE base shear. So inelastic MCE base shear, the green one should be lower than the yellow one. So here the base shear is approximately half of the elastic base shear, but SLE base shear is significantly low. On the right side, it is based on percentage of the weight of the building. So if the green bar is larger than the yellow one, larger than the elastic base shear, our analysis is something wrong. We have to recheck our model. And this is the sample output of the transient drift that we check. The average drift limit is 3%, the solid red line. So the average value is the black line from the ground motion records. And here is the residual drift check. So residual drift we check at the last step of the analysis. For residual drift check, we need to analyze the building maybe 2-3 cycles, at least 2-3 cycles beyond the ground shaking, after the ground shaking stop. Because ground shaking stop, but the building may still shake after the ground shaking. So we need to analyze that effect in our nonlinear time history analysis and check the permanent drift. So the drift limit is 1% for average limit. For individual, it is 1.5%. And for the local responses, we have to check the shear walls, For the deformation capacity requirement, normally we check the axial strains for the flexural deformation, but for the shear response, we check the shear capacity with respect to the shear domain. So here are the sample plots of one location of the shear wall. So at one corner of the shear wall, we have to check all corners of the shear wall. Here is the sample result for one corner. So on the left side, it shows the axial strain, compressive strain of concrete. On the right side, we show the tensile strain of the vertical rebar. So x-axis is the strain value, y-axis is the story level. So compressive strain, for the unconfined concrete, we limit the strain to 0.003. On the right side, we check the tensile strain, but the rebar yielding strain 0.002 is not a limit. Actual limit is 0.05 for the rupture strain. It is very far from that. So we can see that in one ground motion, the shear wall is yielding in flexure at the base. For coupling beams, we have to check the flexure rotation for the conventional reinforced coupling beam. For the shear, we consider as a critical force control action. Normally, when we check the shear in the beams, we check the probable shear based on the capacity-based design approach. For diagonal reinforced coupling beam, we check the shear deformation as a deformation control action. Here is the sample result of one coupling beam along the height of the building. And the black one is the average demand, and the red line is the rotation limit. X-axis is the coupling beam rotation demands in radian. For the moment frames beams, we check the flexure rotation as a deformation control action and shear demand as a force control action. For the columns, we check the axial demand as a compressive demand as a force control rotation for the PMM action, and shear capacity is checked as the force control action. For the flat slab, we check the flexure rotation of the flat slab as a deformation control action. So to model the flat slab nonlinearity, we have to model the equivalent slab beam with the frame element and provide the moment hinges at the end of the beams. Then we check the rotation. That rotation capacity depending upon the punching shear demand to capacity ratio. For the diaphragms, in plane stresses in the slabs, we check the collector, reinforcement, shear friction, chord, and axial and shear. All are force control actions. So for mat foundation, we have to check for the bearing capacity, geotechnical capacity, and also the strength capacity requirements for flexure and shear capacity. So for mat foundation design, we consider all actions as a force control action. For shear capacity, we have to check for the one-way and two-way shear. For basement walls, normally people design the basement wall to resist the lateral pressure for the out-of-plane action. But we also need to check the in-plane response as well, like a shear wall shear. So in-plane shear needs to be checked. So we have to check the both in-plane and out-of-plane shear capacity, and also the flexure capacity, out-of-plane flexure capacity of the basement walls as force control actions. So in PBD, it is that design approach is the evolving topic. So we have to do the continuous learning, and also in our design, we need another person to review our work, which is in which we are doing right or not, because we are doing beyond the code. So peer reviewer needs to be engaged, and not only that engagement will also promote the exchange in the idea and also the knowledge sharing between peer reviewer and the structural engineer of record. And also we can enhance the body of our knowledge for the firms practicing PBT. Normally, peer review should engage at the early stage of the structural design phase. And during the peer review process, peer reviewer develop the peer review comment log and also set up the timing and peer review milestones. So that's all for my presentation about the performance-based seismic design.
So Mr. Zia will be sharing his insights on an overview of wind tunnel testing. So a brief introduction. Mr. Zia is currently the coordinator of wind tunnel testing and structural health monitoring at IT Solutions. Mr. Zia completed his graduate studies in structural engineering from Asian Institute of Technology and specializes in wind engineering, structural dynamics, laboratory instrumentations, and digital signal processing. Mr. Zia is involved in projects of wind engineering, performance-based seismic design, and structural health monitoring. So without any further delay, I would like to give the stage to Mr. Zia. You may share your screen. Thank you very much.
So topic of my talk is wind tunnel test, and I'll just give an overview. Okay, right. So let's talk about some wind effects on tall buildings. So for wind effects on tall buildings, there are three main components. One is cladding pressure. So in this video, you can see the John Hancock Tower, which is around 240-meter tall, six-story building. In 1973, just after the construction of the structure, there was some wind event. And as you can see in this video that some window panes were replaced, and not some, actually a lot of them. And it cost about 5 to 7 million USD. And it happened due to some windstorm. But during that time, there was no mobile device that immediately when it was uh, failing during the windstorm. Nobody could make the videos. The video was made after the event. But these days, we can actually directly see when the event occurs. For example, this video is captured in 2021 in Karachi, Pakistan. You can see cladding failure due to wind. Uh, so this is one of the uh, problem for a building that its cladding may fail. Now, this John Hancock Tower, this building actually had several issues. One of which was building actually swayed in the wind, and upper floor occupants suffered from motion sickness, and it required some retrofitting. For that, they installed two thermos dampers, and that cost them about 3 million USD. And they also have to put bracings to suppress the acceleration response. So in total, 8 millions were invested. So the total cost of the project was about 75 million. So you can see that as they did not consider the wind tunnel test, so the additional cost was about 15 million. So we do not really want that. So it's better to go through some wind engineering work for this sort of a project. Now, how it feels like wind-induced acceleration, you can see from this video. It was captured in 2012 in Denver, Colorado in US. During a windstorm, the building vibrate, and you can see that from the vibration of this chandelier. So it can be quite scary if you are at the 40th floor and you can see the building is vibrating like that. And aside from that, another effect for the wind is the pedestrian comfort and safety. So you can see that these people actually in a certain location cannot really walk comfortably, and can be a safety issue also. When there are tall buildings constructed around, it can create some channeling effect, or tall buildings can create downwashing flow, uh, which can cause this pedestrian comfort and uh, safety issue. Now, we have some design solution for this case. We can have we have building code. I just showed ASCE code, but not necessarily it has to be ASCE, just for an example. And then we can do wind tunnel test. And as well, we can do also CFD simulation. CFD stands for computational fluid dynamics. Now, our building codes have some limitations, but before explaining that, I need to explain the concept of wind-induced response, how it is accounted. So here I'm showing two time histories. Let me do this. Okay, this one is the force time history, and the next one is the conventional and response time history, you can say. So mean force actually gives mean response, and fluctuating forces actually give fluctuating response. We call it background response. But this fluctuating force actually have frequency content. When it matches with the natural frequency of the structure, our structure start to vibrate. And vibration of the structure actually generates inertia force. So the total response can be even higher. So the total response is actually coming from the mean force, mean response. Fluctuating force is giving background response. And then this inertia force actually gives resonant response. So this is the basic concept of wind-induced responses. Now we can start looking at the limitations of the building codes. I'll explain few of those for today's presentation. So one limitation of the building code is it cannot account for the interference effect. For example, in building code, they consider exposure D, which means like open sea or flat terrain. And then they have exposure C, which you can say open terrain. It assumes that there are some small houses in front of your structure, but none of these are taller than your structure. And there are no buildings at the back of your structure if the wind is coming from this direction. This is the assumption in the building code. And they have exposure B, which means suburban terrain. So a bit more taller buildings in front of your structure, but none of them are taller than your structure. And there is no building at the back. But in reality, our structure is actually surrounded by structures of many different sizes and shapes and so on. And due to these structures, there is an effect called interference effect, and that is not accounted by the building code. And what it does is like it actually reduces the mean response. Some people call it shielding effect. So for example, if there is a structure in front of your structure, then there can be some shielding effect for which the mean response can reduce. But we often observe that it can actually increase the background and resonant response significantly. So overall response can be actually higher than previously, let's say, estimated where there is no surround building. So interference effect can significantly increase the building response. Well, in some cases, it can reduce a bit because if the mean response reduced significantly, then the total response can be reduced. But in general, it increases. Now, you may say, how about if we do some research and come up with an interference factor, and then we can use it in the equivalent static load so that we can account for the interference effect. For example, if this is your target building, we can put an interfering structure at the back or maybe at the front, or maybe we can put multiple interfering structure, one at the front, maybe two at the side, and so on. And then we can get response with interfering building and response of isolated building, and we can estimate an interfering factor, which we can incorporate in the building code. We have done a lot of research in AIT as well, but problem with that is our city is quite complicated. For example, if this is our target structure, it can be surrounded by many different structure of different size and different shape. For that, this interference factor may not really work. So that is why even though the research on the interference effect started in somewhere in 1920, I guess. But still, there is no interference factor you can see in the building code because our city is a bit complicated. And then moving on, another thing is the building shape. For example, this project is located in Philippines, so we worked on this project. It is given a shape of a Christmas tree. Well, our building code can actually estimate wind-induced forces for, if I say building, for specifically rectangular buildings. But if you have a building of a bit not so conventional shape, in that case, even though the building may not be so tall, you might have to go through the wind tunnel model test because you cannot really use the building code approach for wind-induced forces. And then how about a very conventional rectangular building? For example, in this case, a CRC building. We just want to figure out how it responds to the wind. So we measured pressure in the exterior surface of this rectangular building, and then we plotted a pressure contour, a dynamic pressure contour. So this one is the front, and this one is the right, back, left, and wind is coming from the front side. And this is the fluctuating pressure that we have plotted. And then we have shown drag force, lift force, and torsion, torsional force coefficients. What we can see from here, even though the wind is coming from the front side, as Mr. Aung discussed about earlier, wind is coming from the front side. So our expectation would be like the force would be only Fy. But we can also see the force Fx. This sort of a force is called across wind force, or for that, the structure will have across wind response. Most of the building codes does not account for the across wind response. Even if any building code accounts for that, they cannot accurately estimate the across wind responses. Another thing is, if you see the fluctuating pressure, you'll see the pressure is higher in one side sometime, then sometime it is higher in another corner, and then the distribution of the pressure is not uniform. And due to the non-uniform pressure, we can have wind-induced torsional response. So this is also not accounted in many of the building code. So in general, what happens is the building have to resist along wind response and torsional response at the same time. So we call it lateral torsional coupled response. So which we can actually account in our through the wind tunnel model test, not by the building codes. And aside from that, there are some other limitations in the building codes. There are some limitations on the height. There are some limitations on the natural frequency and so on. Now moving on, so the best solution that we can get as of now is the wind tunnel model test. So in the wind tunnel, what we do is we simulate the natural wind in a smaller scale. So I'll explain further. So we have spires and roughness elements. So we have a fan that generates a smooth wind. And when it goes through these roughness elements, we can have boundary layer wind. Then in the upwind location, we have the scale down model, and we also model the surrounding structures. And surrounding structures are to account for the interference effect coming from these surrounding buildings. And then we have the target structure. And from the measurement, we can get structure wind load, we can get cladding pressure, and we can also get some estimation on the pedestrian comfort and as well as for the safety. Now, this is our wind tunnel in AIT. This is about 23-meter long, and it can produce a wind speed of around 20 meters per second. This is one of the largest wind tunnel in the Southeast Asia zone. And in this wind tunnel, we have tested several structures. Over 50 projects we have done, and many of our projects are located in Philippines. Some are located in Cambodia, Pakistan, Thailand, and so on. And the height range is like from 100 meter to about 350 meter tall buildings that we have tested. And not only the buildings, we have also tested some complex structures like statues or bridges or even submarine ships and so on. And now I'll explain how this wind tunnel test is actually carried out. So we simulate the boundary layer wind. So we have these spires located at the back. And then on the floor, we provide some roughness elements to simulate the boundary layer wind. This dimension of these elements are actually decided based on trial and error so that we can match the mean wind profile and turbulence intensity. So these two parameters we have to match so that like the wind profile at the site, we can achieve it in the wind tunnel. Now, how we get the wind profile at the site? We can do it through the climate analysis. We have some software to do the climate analysis and identify the site-specific wind profile. And these two are the parameters that are used to identify the wind fluctuation and wind profile in the site location. Then we test actually for several configuration. For example, the figure at the left is showing the existing surround configuration. So this is our target building. Okay, this project is located in Karachi, Pakistan. So, and these are the existing structures. So in this location, this structures already been constructed. So we consider for this surrounding configuration. And then we also consider the future surrounding configuration because the client, they could provide us the information for some future construction in that location. So these buildings are also incorporated. So we tested for the existing surround and also for the future surrounding, and then the design can be done for from the envelope that is okay. Then in some cases, we find out that, okay, there are some very tall buildings which is outside of the test zone we have. In that case, we can also model these tall buildings which are far from our target site so that we can accurately capture the interference effect that can cause some effect on our structure as well. Now, how the test has been done. First, I'll talk about the high frequency force balance test. So in this case, we make a high density foam model, which is very lightweight, and it has been supported by a carbon fiber pipe section. So the stiffness of the model is normally very high. We try to keep it over 100 Hertz. The name of high frequency force balance, high frequency comes from the high frequency model. And then we have a force balance at the bottom, which is a force sensor. And from from this sensor, we can actually estimate the wind-induced overturning moments and forces at the base. So at first, we get the measure the forces. As we measure the forces in model scale, we have to estimate the force coefficient, which is unitless. And from there, we can estimate the prototype forces. Now, this prototype force actually have the mean and background component. It doesn't have the resonant component to it. So we numerically add the resonant component, or we use the frequency domain approach. And then we can estimate equivalent static force along the height. So here I'm showing equivalent static force forces for 700-year return period. We can get the force Fx, Fy, and also torsional moment. This is for the ultimate strength design, but we also provide service level forces also for 10-year return period, and we also estimate acceleration response for 1-year return period. Now here I am showing some results of some tests we have done. So X line is like the number of projects that I have shown here. So here I have shown 31 of our project result outcomes. Now, this red dash is like baseline. This one is like, these dots are actually ratios of wind tunnel test and core prediction based overturning moment. MX is represented by green dots and MY is represented by blue dots. So this is the ratio of wind tunnel test and code prediction. So if these ratios are within this red line, it means like whatever the result we have obtained from the wind tunnel test are actually matching with the results from the code prediction. But you can see the most of the cases, the forces we obtain from the wind tunnel test are actually lower than 1. It means from the wind tunnel test, you can actually achieve a bit economic design. But still, those results are safe because in the building code, the force coefficients or the pressure coefficients, those are given, are actually for a synthetic scenario, and those are coming from the wind tunnel model test as well. But if you test your actual structure in the wind tunnel, you can get the actual result. So in that case, you can achieve a much economic result design, or in some cases, you can see that is forces are much higher. It can be even 1.4 or 1.5 times higher. In this case, you have to think like the results you are getting. Actually, this is giving you safer outcomes because in the winter, for the building code, it did not account for the interference effect and some other effects, which is accounted in the building code, which is accounted in the wind tunnel test. So the forces you have achieved can be sometimes higher also because of those effects. And then here I have shown two of our projects. One is at the left is in Cambodia. It is about 322-meter tall building. And at the right is an observation tower located in Philippines, which is about 200-meter tall. So this sort of a structure actually have a much higher acceleration response. So now I'll talk about some acceleration issue and how we can mitigate those. Not only these tall buildings, even a shorter structure, in this case, a structure located in Karachi, I'm showing like it had very high acceleration response. It height was only 150 meter. And then, as I explained earlier, this structure was tested for existing surrounding scenario and also for the future surrounding. For the existing, the acceleration response was high for most of the wind attack angles, but for the future configuration, it was significantly higher than the limit. Now here, I am showing the acceleration response for 1 year return period, and the limit I'm talking about the ISO acceleration limit for residential building. It's a residential project. Initially, we find out the acceleration response is about 1.81 times higher. Then we assume that, okay, how about if we increase the stiffness of the building by 1.6 by 1.5 times by adding bracing or maybe increasing the shear wall dimension and so on. But what we find out, the acceleration response have reduced a bit, but still it is about 1.63 times higher than the limit. Now, if you see the limit, you can see in the x-axis is the natural frequency. So when the natural frequency is low, it means when the structure is less stiff. In that case, you have higher tolerance for the acceleration. But when the natural frequency actually increases, which is increment of the stiffness, the limit actually reduces also. For example, the idea is when the acceleration is high in the higher frequency, and then when actually the acceleration in the higher frequency have lower in terms of tolerance, and that is actually identified through some shake table test. Some experts are exposed to acceleration of different frequency, and then they give their opinion on which frequency, how comfortable or how discomfort they had the feeling. Based on those, actually these parameters are set. So you can see for the higher frequency, the acceleration limit is a bit lower. So solution for this one is applying damper to the project, to the building. So for this particular project, we actually assigned two dampers. One is to suppress the translational acceleration, and another is to suppress the torsional acceleration. And as you can see, this green line is actually acceleration response and this when there was no damper to the structure. And this red line is the limit, which is about 8 millig for this coming from the ISO criteria. X-axis is actually wind attack angles. We test the structure for 36 wind attack angles. So wind attack angle from 0 to 350 is shown. So almost for all the wind attack angles, you can see the structure had higher acceleration. And after we applied damper to the structure, the acceleration actually suppressed. Only at the 90-degree due to the across wind response, the acceleration found to be slightly higher than the limit, but it's still acceptable. Now for the dampers, there are many different types. Now for two-mass dampers also, there are many different ways to apply those. For example, there is a pendulum type two-mass damper installed in Type 101, which actually occupied about 6th floor. Actually, for a 150-meter tall 50-story building, this is not a economic solution. So in AIT, we did some research and we come up with a multi-stage steel laminated rubber bearing two-mass damper, and we find out that this type of two-mass damper actually can be more cost-effective. It can save valuable floor space. So this is about the structural wind. So I talked about the forces, I talked about the acceleration. Now we'll move on to the cladding pressure study, which is another important fact. So for this one, we actually have to make a different type of model. So we use 3D printers to make this sort of a model. And then we install pneumatic tubes to this model. And those are connected to the pressure sensor so we can get the measurement. And then we test this one for 360-degree wind attack angle with the interval of 10 degrees. So for 36 wind attack angles, we test. And then we obtain cladding pressure outcomes. So here I'm showing peak pressure, peak positive pressure for this particular project. It is located in Pattaya in Thailand. I think it's very popular. Most of you already know about it. So the project was nearby a hill. So inside the wind tunnel, we also model the small hill. In case of small hills, we can model those in the wind tunnel, as you can see. And then we can also obtain the negative pressure cladding designed for positive and negative pressure. Now, cladding pressure study can be handy also. It can be used to estimate wind-induced forces as well. For example, this project located in Bangkok, it had a very long cantilever at the front here. It is about 24-meter long cantilever. Now, this cantilevers, due to the cantilever's location, we could not do the high frequency force balance test, as you can see here, because we cannot put the force sensor here. So we measured the pressure and we used another approach, which is called high frequency pressure integration, HFPI, to estimate the wind-induced forces for this cantilever section of the structure. So we use the cladding pressure. We measured the cladding pressure, and then we use HFPI technique to estimate forces for some location. And this pressure measurement can be handy for projects like this dome structure. So this one is a temple located in Saraburi, Thailand. So we measure pressure in 79 tap locations. And then this is the pressure contour. So once we measure the pressure, we apply this pressure to finite element model, and then we run the linear time history analysis for the design of this structure. And this structure is already been constructed and open to public, as you can see from this picture. And then there are some structures like stadiums we worked on recently in Philippines. So we had two structures here. One was an exhibition hall, another one was a stadium. We used the same technique to get the wind-induced forces. So we measured the pressure, and measure pressures were directly applied to the finite element model, and then the structure was designed. Now, you can also run the nonlinear time history analysis using the wind-induced pressure if you wish to do the performance-based wind design or not. the same concept can be applied for that. Now, aside from pressure measurement, one last thing we do is the environmental wind study. So we are back to this tree-shaped structure. Here we actually place a different type of sensor. We call it, actually it is called Arwin probes, but in AIT solution, we call it Swapit probe. Swapit is one of our colleague who actually construct these sensors. So there are some sensors that we can also construct in AIT. Then, so okay. From this sensor, actually, it represents a human being of height 1.5 meter. So we measure pressure at the top, which is called dynamic pressure, and we also measure pressure at the bottom location here. So that is static pressure. So from the pressure difference, we can estimate the wind speed. And from there, we can identify if there is any discomfort zone in and around the building. For example, in the outside or maybe in the roof or in large balconies. For example, these dots are the locations where we have done the measurement. So we had the probes in this location. So in some location, we find out that the wind speed is good enough for the pedestrian sitting. And we identify that one through by comparing our outcome with the Lawson criteria, which is available in the public source. And then we identify some location is pedestrian standing, some location is pedestrian walking, and so on. Now, if we can find some location, for example, here, if we find this one is uncomfortable for all users, in that case, we can actually apply windscreens, or we can plant trees around to reduce the wind speed. And that is the reason why you can see some shopping malls, specifically in Bangkok, if you come, there you can see many trees are planted here and there, may look like randomly placed, but those are actually coming from the wind tunnel test outcomes. So you can suppress the wind speed and make it comfortable for the users by planting trees or putting wind screens around. So that's all for the wind tunnel test. Now, another thing we can do is computational fluid dynamics simulation, CFD. So with the CFD simulation, you can achieve all the results that you can get it from the wind tunnel. You can get structure, wind load, cladding pressure, and also pedestrian comfort. But CFD have one limitation. Limitation is like you are modeling the wind based on some assumptions in your software. Okay. In the wind tunnel, we are testing in the wind tunnel, so we do not have to assume the wind property and so on. But here, as you are modeling in your computer, so you have certain assumption on the wind, wind flow, wind structure interaction, and so on. So that is why till this date, wind tunnel test is more preferred over the CFD simulation. But some clients come to us to do some environmental wind study using CFD simulation. So anyway, we can do the CFD simulation, but we need to be very cautious about it. Now, my presentation was mainly on the building structure, but there is another structure which is bridge structure are more vulnerable to the wind, and in the building code you may not find any information for the design of these structures. So for example, in the left hand side you can see Tacoma Narrows Bridge. It collapsed in 7 November 1940. It collapsed due to a phenomena called torsional flutter. So due to a very low speed wind, about 90 meters per second, this bridge actually collapsed due to the torsional flutter. And at the right, you can see the movement of the structure in vertical direction. So excuse me. All right. So if you notice carefully, you can see this bridge is actually vibrating in vertical direction. Okay, so these two are very important factor for a bridge. One is the torsional flutter and one is the vertical movement. But we can identify these motions through the wind tunnel test. So this is one of the project we worked in Philippines. So we give some initial vibration to the structure, and then we identify negative aerodynamic damping, which actually causes the torsional flutter and also the vertical motion of the bridge. And that actually negative aerodynamic damping means once your structure starts to vibrate slowly, and due to the wind, the vibration actually escalates. It actually uh, significantly amplifies and then come to a point then when the structure actually fails. And we can identify it through some flutter derivatives. We call it A2 star for torsion and H1 star for the vertical motion. And if we identify the structure is vulnerable, the bridge structure, then we can actually do some modification in its cross section. For example, this one is a bridge structure in Thailand. It's called Rama 8 bridge. So after the wind tunnel test, it was find out that the structure may not be the bridge structure can be vulnerable. So then the bottom part was enclosed, and so that it can give some aerodynamic shape to the bridge structure. And this bridge is in Japan. It's called Ajigawa Bridge. So you can see this aerodynamic shape is given to the structure so that it is less vulnerable to the wind. So yeah, that's all it is from my side. And thank you for listening. Thank you so much.